Now let's apply this trick to prove these two theorems. And actually, I'm going to just prove this theorem. And the rest you can find the van der Monde identity in the notes. I will only do the trinomial revision formula here. So now let's derive the trinomial revision. So let's use the polynomial identity trick to derive the trinomial revision formula for NAB in C from the version for NAB in N. So we proved it for N, and now we want to derive the case for C. So I'm going to repeat this formula just so that you have it on the same screen. There. This is what we know, and this is what we want to prove. So proof of the theorem. Okay, let NA be in C. First of all, I'm going to get to make some W log assumptions. If B is not a non-negative integer, then this equality boils down to 0 equals 0. So why? Because A choose B is 0 and N choose B is 0. Remember, a binomial coefficient with whose denominator is not an N. I should not say denominator, but that's how it looks like. In this case, B is not an N. Such a binomial coefficient is always 0. So W log assumes that B is an N. We haven't used the trick yet. So we have we have made some steps towards this case that we know. We now know that B is an N, because otherwise you have 0 here and 0 here, and 0 is of course 0. Next, if A is not an N, then the same is true. Again, you need to prove that 0 is 0. Why? So N choose A is 0, that's clear. And now, what about this one? Well, A minus B. If A minus B was a non-negative integer, then A was would be a non-negative integer because B is 1. So if we had A minus B is in N, then we would have A is A minus B plus B, so A minus B is in N. And B is also in N because we just assumed it a line ago. So A would be in N, but A is not in N by assumption. Okay, so this is also 0, and so again we have a 0 factor on each side, and so we're proving 0 equals 0. So, without loss of generality, assume that A in N. Great, we are 2/3 of the way. We have reduced the theorem from the case NA, B, and C to the case when N is in C, but A and B are non-negative integers. Now, how can we make N a non-negative integers? Unfortunately, the equality in question is not in any way obvious when N is not a non-negative integer. Sad but true, we don't have N in the denominator. So if N is, let's say, square root of 2, these numbers will usually be not 0. So we cannot get rid of this case so easily. Here the polynomial identity trick comes in handy. How to do this? We define the following two polynomials. P of x is the left-hand side, except n becomes x. Q of x is the right-hand side. Why are these polynomials? What does this even mean? We have never so far substituted an indeterminate into this binomial coefficient. We have substituted variable integers or numbers, but they have always been numbers. X is just this formal symbol. What does this even mean? Well, what could it mean? You take the definition of a binomial coefficient, so x, x minus 1, and so on, x minus a plus 1 over a factorial. and just plug this variable x into it. And a choose b is just a choose b, nothing weird going on here because a and b are just non-negative integers. Now on this line, you have two binomial coefficients with x on the top. So again, you follow the definitions that you know. Now, this is a bit tricky because there are cases. A minus b can be in n or not in n. So if a minus b is in n, then you get this x minus b minus 1, and so on, x minus b minus a minus b plus 1 over a minus b factorial. And if a minus b is not in n, then it's just 0. That's our old definition of binomial coefficients. All we've done here is we've extended it in the most obvious way. We're allowing to plug an x instead of, or an x minus b instead of the n. So our proposition above, this one, tells us that P of n is Q of n for each n in n. Why? Because this is P of n and this is Q of n. If you plug an n for an x in this polynomial, of course you get n choose a times a choose b, because all those x's become n's. And if you plug n for x in this polynomial, you get this because all the x's here become n's. And therefore, so this means that P of n is Q of n for infinitely many n's, because there is infinitely many non-negative integers. Thus, by the polynomial identity trick, we have P equals Q, and therefore P of n is Q of n for all n in C, not just for the non-negative integers, but for any kind of numbers. And this is exactly saying what we want here. So the theorem is thus proved. So, in retrospective, what have you done? We have started with a proposition that's specifically about non-negative integers, and we have turned it into a theorem that says the same thing, but for any numbers. How did we do it? We gradually reduced the general theorem to the particular proposition. First, we argued that the number b is without loss of generality a non-negative integer because the other case is obvious. Then we argued that the number a without loss of generality is a non-negative integer because the other case is obvious. And finally, with a and b being fixed non-negative integers, we argued that the identity in question is a polynomial, is an equality between two polynomial functions in n. And if you want to prove such an equality, it suffices to prove it for non-negative integers, because there is infinitely many of them. So we have derived the general trinomial revision formula from the particular case we proved above. We proved by double counting. Remember, committees and subcommittees. Using the polynomial identity trick. So it is pretty important to not forget, we did not apply the polynomial identity trick to a or to b. We applied it to n, because a and b appear in the denominators of these binomial coefficients. And then the trick is taboo. If you try to plug an x in the denominator, it makes no sense. The only place where you can put it, you cannot take x factorial. The factorial makes sense only for non-negative integers. So note that we used the fact that n choose k is a polynomial function in n for fixed k. If you multiply it out, it's like n times n minus 1 times and so on. It's pretty clear. It's a polynomial of degree k, actually, when k is a non-negative integer. So this allowed us to replace this n here by a polynomial variable. However, n choose k is not a polynomial function in k for fixed n. Why not? Well, easiest way to see it is if k is a non-negative integer, this can be non-zero. But if k is negative or not an integer, it's zero. A polynomial cannot behave this way. A polynomial, if it's zero infinitely many times, it would be zero for all k's, which is absurd. So while we were able to replace the n by x in the above proof, we could not have replaced a or b by x. This is why when we were reducing the b and the a to non-negative integers, we could not have used the polynomial identity trick. It worked for n, so. And a and b were easy. So the polynomial identity trick is not a panacea. You cannot just pick a random variable in your identity and just say, okay, now let's make it a non-negative integer. It has to be a variable in which both sides are polynomial functions. Now, as I said, I'm not going to prove the Chu-van-der-Monde identity, but the idea is the same, except you have to apply the trick twice. You apply it to x, so you keep y fixed, and then you apply it to x to make sure that x is a non-negative integer. And then once x has become a non-negative integer, you do the same for y. So it's like leg after leg. You first change the x and then change the y. So the Chu-van-der-Monde identity in the general case has a similar proof, which, however, uses the polynomial identity trick twice. Once for x and once for y. See the notes for details. See the notes also for, well, I should probably just edit here. See the notes for some warnings about how not to apply the polynomial identity tricks. I mean, some more warnings. It is tempting to, for example, throw it at this here, the hockey stick identity. We had this on the homework. But you cannot. Neither side is a polynomial in k. Actually, it's enough that one side is not a polynomial in k, but neither of them is. And you cannot replace n by a non-integer either, because what would the sum be if I had square root of 3 here? What would this even mean? It makes no sense. So you cannot just pick anything and generalize it to real numbers, but a lot works, and this can be very useful.